we're going to talk a little bit about what is a chemical reaction. And at this point, you should be silent and paying attention up here. Okay, so chemical reactions occur anytime matter interacts with other matter to create yet another new type of matter. Anytime matter interacts with other matter to create yet another new kind of matter. So I used to have ninth graders watch a video. It was made in like 2005, but the video was like 20 minutes long, and the narrator said matter roughly 200 times in that 20 minutes. It was informative, but rather miserable. So we didn't make you guys watch it this year. All right, so anytime matter interacts with other new matter to create yet another new kind of matter. This happens through changing valence electrons or exchanging valence electrons. Exchanges of valence electrons. Or this could occur, and this occurs through changing bonds between atoms. Changes bonds between atoms. You guys are doing that. Good. All right. So when we talk about a chemical reaction, we can represent that on paper using what we call chemical equations. Chemical equations are basically a mathematical way of representing what happens in a chemical reaction. In a mathematical way of representing a chemical reaction. A chemical reaction. Right? Structure for a chemical equation. So if in our equation we have, let's say, some element x plus some element y, and it reacts to produce some combination x, y. Anything on the left-hand side we would call reactants. Reactants. And anything on the right-hand side we would call products. So the reactants are what you have before the reaction, and the products are what you have after the reaction. Before reaction, after reaction. And when we read the chemical equation, we see the arrow here as reacts to produce. Reacts to produce. So chemical X and Y react to produce compound XY. Okay? Reactants. T-A-N-T-S. Okay? So when we are talking about chemical equations, the ones we're going to be working with this chapter fall into 5 different categories. The first category are synthesis reactions. A synthesis reaction occurs whenever we take 2 substances and they combine to make a more complex substance. When 2 substances, somebody should warn me when I'm getting to the bottom of the page like that.
All right.
Yeah. Reactants, they exist before the reaction. So when 2 substances combine to form a more complex substance. The general form of the reaction looks something like A plus B reacts to produce AB, which is kind of the example I gave above. And if we want to talk about a real life example, we could talk about, well, rocket fuel. So if we take hydrogen and we add oxygen to it, and we spark that, then those will react to produce water. So when we were launching the space shuttle up into space, this is actually how we would do it. We would take hydrogen, well, liquid hydrogen and liquid oxygen, put them in the same tank together, well, pipe them into the same area together, spark them, and these two explode. And when they explode, we could lift the rocket off the ground. One of the nice things about using hydrogen and oxygen is the byproduct, or the exhaust, is just liquid water, or steam. So all we produced when we launched rockets into space was steam, and that's not terribly dangerous. Okay? Now, we could have synthesis reactions as our first option, and our second option then would have to be decomposition reactions. Decomposition reactions. Now, decomposition reaction is the opposite of a synthesis reaction. Opposite of synthesis. Okay? When we say it's the opposite of synthesis, that means that we're taking a more complex compound and breaking it down into its component pieces. A complex compound breaks down into simpler substances. Into simpler substances. So if it's the opposite of synthesis, what do you want to take a guess the reaction looks like in terms of its general form?
Like, not good. Right?
Say again?
So it's not good because you said the first one was like good. Like, I guess. You know?
I'm not sure I follow you.
Okay. Never mind.
Yeah. I'll do A plus B, but yeah. AB reacts to produce A plus B. And if we want to use this in terms of an example, we can talk about water. H2O reacts to produce 2H2 plus O2. So in the first one, we could combine hydrogen and oxygen to produce water. And in this one, we can take water and we can split it apart into hydrogen and oxygen. This is a process that we call electrolysis. And works by putting electricity through water. Do not try putting electricity through water at home. Not a good choice. So we'll do it in class. Okay? So we can take water, break it apart into hydrogen and oxygen. Our next type of reaction are single replacement reactions. If I can write, replacement reactions. In a single replacement reaction, we take a compound and we basically swap one part of it out for a different part. So one component of a compound is replaced by a new one. Is replaced by a new one. As a general form, that would mean that A plus BC reacts to produce AC plus B. Now, when we're talking about ionic compounds, metals replace metals, nonmetals replace nonmetals, and if, let's say in this case, A was a metal, it would look like AC plus B. But if A was a nonmetal, it would have to replace the piece at the end. So it could also do, or BA plus C. So depending on what each of them were, what A was, it could replace either B or it could replace C for different reactions. The lab we're going to do on this one
is going to be iron plus copper sulfate reacts to produce iron sulfate plus copper.
So you're going to wind up starting with a nail, adding copper sulfate, allowing the reaction to produce iron sulfate, and you'll get pure copper out. Okay.
Next one up. So if our synthesis and decomposition reactions were related because they're opposites, then our next two are related not because they're opposites, but rather because we're going to simply add one more element into the mixture. We're going to have double replacement reactions. Anybody want to take a guess at this one?
Well, one component from two different compounds replace each other.
All right, so one component, and I'm going to just say swaps, with a component from a different compound. A component from a different compound.
And a guess at the form of the equation?
It's a guess, so it doesn't hurt to be wrong.
We're all still writing.
I'm still writing. So right now we're looking like our old equation. Oh, so we can add a D here.
Oh. So now it's like A.
I want to keep the C first. So all we did here was swap the back half. Yep. Like. All right, so I'm going to go ahead and put down an example for this bottom one. So let's say we've got magnesium chloride plus sodium oxide reacts to produce magnesium oxide plus sodium chloride. And you'll notice all that we did was we swapped part B and part D. So where we had chlorine before, oxygen's now been attached. And where we had oxygen before, chlorine's now in that position. This two right here, we'll talk about that in a minute. That's why. Yeah. Yeah, that's we're gonna get to that in like 3 minutes. So give me a little time. Minutes, not seconds. All right. So, questions about single or double replacement reactions? All right, so this one Taylor should be a little bit happier with because I'm going to be able to give an example she's probably very familiar with.
Next type of reaction is combustion.
A combustion reaction is simply any reaction that takes a carbon-based compound, reacts it with oxygen to produce carbon dioxide and water.
Any reaction that takes a carbon-based compound, there's an R in there, and oxygen, and produces water and CO2. And the form of our equation then would be some kind of carbon, and typically it also involves hydrogen, plus oxygen, reacting to produce water, CO2, And what's a big deal when you have a combustion reaction? What's the purpose usually if you're trying to involve yourself in a combustion reaction? Why would you ever use one?
I've never been perfect.
Because you're wanting to start something on fire. All right, why do you usually want to start something on fire? To produce heat. So to cook something, because you're cold. Either of those answers, you want heat. Okay? Yeah, plus heat. So, for example, we could take something like C3H8 plus O2 reacts to produce H2O plus CO2 and heat. Now, I'm probably hearing from the backs of your minds, I'm not familiar with that. I don't know what C3H8 is. I don't have that as an example. Sure you do. C3H8 is propane. So anytime you burn propane, like on a grill or in a heater, you're combining it with oxygen to produce exhaust, that's water vapor and carbon dioxide, and heat.
So it wouldn't be flammable in space?
No, because you kind of need oxygen.
Yes. Okay.
Okay? So, big detail here that I want to point out, and this one's frequently not recognized. Everybody understands that if you burn stuff, you produce carbon dioxide, right?
Yeah.
That's something that we generally know. But when you burn things, you also produce water. Okay? So steam is actually a byproduct of burning things. Right here? This one right here? That's an 8. Okay? All right. So I'm going to leave that equation like this for just a moment. And I'm going to leave some blanks here. Because when we are talking about chemical reactions, all chemical reactions obey the law of conservation of mass. So all reactions obey the law of conservation of mass. Of mass. Okay, well, what's that? The law of conservation of mass tells us that matter can not be created and cannot be destroyed, but it can change forms. So when we have a certain amount of matter, whatever we do to it, we have to wind up with the exact same amount of matter, no matter what we're doing to it. So matter can neither be created nor destroyed, but it can change forms. So if we're talking about our example from up here, let's say instead of propane, our combustion, we're talking about, let's say you're burning a log fire. Do you destroy the log in this process?
Yes.
Do you destroy the matter the log is made out of?
No.
Okay, so where does it go?
In the ground.
Into the air. Say again? Okay, we get ash. What else do we get? Smoke. Smoke that's made out of carbon dioxide and water vapor. Okay? If you were able to collect all of the smoke from a log that you burned, and you measured the mass of all of the smoke from the log, and you added it to the mass of the ash left over, you would get the same mass as the original log. Yeah, it's kind of tricky, but it has been done. And you do use a vacuum chamber.
Oh,
Yep.
like that thing you used to open the chips or whatever.
Yeah, like the thing that we use to open the chips.
Do you remember this? Do you remember this and then like we went into her room and like she had
All right, so when we're writing chemical equations, one of the things we've got to do is actually show this law to be true. That way we're making sure we're not just creating things out of nowhere. So using our example from above, C3H8 plus O2 reacts to produce H2O plus CO2. And I'm going to leave out heat for just a moment because heat's not an element. It's energy. Yep. So what we're going to do is we're going to take a look and see how many elements of each type we've got on both the reactant side and the product side. Then we're going to add coefficients to make sure that they're the same. So on the reactant side, how many carbon are there?
3.
How many hydrogen?
8.
How many oxygen?
2.
How about on the product side? How many carbon?
1.
How many hydrogen?
2.
How many oxygen? Everybody good with that? Okay, so now what I'm going to do is I'm going to add coefficients to balance these out. So like I see I've got 3 carbon over here. I want 3 carbon over here. So I'm going to add a 3 right here. Now, I've changed the number of carbon to 3. Have I changed anything else? What'd you say? No, I have. I have changed something else. Why the oxygen? So this is saying we have 3 sets of CO2. Not only do I have 3 carbons, but now I have how many total oxygens? 6 and 7. I've got 3 groups of 2, so that's 6, plus this guy over here for 7. Okay? That balances my carbons. Let's balance the hydrogens. Well, I have 8 there, so I need more here. I'm going to put a 4 here. How many hydrogen do I now have? How many oxygen do I now have? Nope. How many total?
18.
10. I've got 3 sets as 2, so 6. 4 sets of 1 for 10. No. Because we were just saying it's 4 times 1 for 4, 3 times 2 for 6, for a total of 10. Last thing I need to do, what coefficient am I going to add? 5 to the O2, so I have a 10 sets of oxygen. And now this is balanced, showing that it conserves mass. Now, a couple of things. First of all, when we're balancing equations, we can change coefficients. Coefficients can be changed. What do coefficients tell us? How many sets or how many pairs? Yeah, absolutely. You guys first encountered coefficients on that build a molecule fence when it had like 4H2 or 3N2 or 2 CO2. It was telling you how many of that molecule or of that compound. Why can't we change the subscripts? It would change the thing, yeah. So more specifically, it would change the substance we're working with. We can't change the subscripts because that's the identity of the substance. Coefficients change how much it is. Subscripts change the identity. So coefficients change quantity. Subscripts change identity.